Here we go. I believe there's a picture that has like a little moving part to it in your book on page 1797. If you need to really see how inscribed angles and tangents play together, how it makes sense, take a look at that and move it around. You'll be able to see, well, I think they move it for you actually. But it just shows you how you get an inscribed angle and a tangent with it and how they really are the same thing, okay? But I can't show you that on here while I'm recording, so you'll have to just go take a look. Here is what we're doing with this section. You will have a chord, just like we did in the first one, but now instead of another chord to form our inscribed angle, you're going to have a tangent coming off of that point. So coming off of this point down here, you would have a tangent line. Okay. So now my angle is this angle. The rule is treat that like an inscribed angle. It looks a little bit different because you have the tangent now, but the rule is the same. That angle is half as much as its intercepted arc. Where I think people have a little bit of trouble is figuring out what the intercepted arc is, because the arc goes all the way to the point, right? So this point right here and this point right here are where it hits our circle. So your intercepted arc for this angle is this. Okay, it goes all the way to the vertex of the angle. So, like I said, the rule is the same. If this is B, we'll put a D here, and C, we would say the measure of angle C is going to be half of the measure of arc BDC. Okay, so you take that arc BDC, you cut it in half, and you get your angle. Okay, so I'm going to give you just 2 problems like this, and if we need to do more, I can do more with you individually, but this is what you're going to be doing with it. This is like example 3, just continuing from our last one. So if I give you a circle, and we have a tangent line here. Oh, that was good, guys. When do I ever actually nail the picture? That is good. Thank you. Well, I appreciate the clap I got. Now my cockiness is going to throw me off. So let's say you have A, B, C, D, and E. Okay. Here's what this problem says. AC is tangent. Okay, AC is tangent to the circle. The measure of arc BED, how many of you would rather be there right now? Yes, is 214. What is the measure of angle DBC? Okay, so arc BED is 214. That means this arc here. Okay, that arc is 214. Ooh, we're moving. Sorry. Okay. What is the measure of angle DBC? So we're looking for DBC, which is this angle. What do you do?
You'd have to subtract 214 from 260 divided by 2.
Right. So if we take this as our intercepted arc, because it is, you would do 360 minus the 214 to get the measure of arc DB. Right? So subtract that, you get, what does that come out to?
DB is
146. So that's the measure of arc DB, and then what do you do to that? Cut it in half. So half of 146 gives you the measure of angle DBC, which is 73 degrees. Now, question for you. Did anyone have a different idea before Landon said what he said? Do you see another way you could do it?
yeah.
How?
We can just grab the measure of angle DBA and use 80 to 180 to just minus it.
Right. Okay, so here's your other option. We know this is 214, which makes this angle 107, right? This is a straight line, so that's got to add up to 180. So you could do 180 minus 107. Notice you still get 73. Okay, so it's your pick. Which one makes more sense to you? Which one you like better? Yes? Because this arc is 214, right? So you're taking that 214, cutting it in half, because that's the inscribed angle for that arc, and 107. You two are just horrible to each other, always. Okay, last one. This one's a little more complex. There's a lot more going on here. I will see how well I can draw this for you. All right, so you have a tangent here that didn't touch, but pretend it did.
Wait, is this still kind of example 3?
You can call this example 4, sorry.
Oh, okay. Sorry.
It really is the same idea,
Okay.
but. All right, so we have right here is J. This is point K. This is L. This is Q. Oh, I missed. Okay. Down here is Y. Angle Q is 35 degrees. And this angle here is X degrees. A little fancier. Do you see a way to find X or a way to find Y? How?
Y, you can go, because angle J is 90 degrees, and so you add 90, like 125 maybe, if I did that math right, and you subtract that from 180, and that will give you Y.
Right. Y is J 90.
It's like a semicircle.
It opens to a semicircle. So if you look at this as your inscribed angle, it opens to a semicircle. Remember, I said several times, look for a diameter, because diameters are huge in this type of problem. So because it opens to a semicircle, which is 180, that makes this J 90. And now you have a triangle where you know two of the three angles, right? So you would do 90 plus 35 plus Y equals 180. So take away 125, and Y is 55 degrees. Okay, so there's Y. How can you find X? Mm-hmm.
How'd you do that? No, not one.
Yeah, and then, K open is a inscribed angle, or we can,
K is not inscribed.
oh, no.
K is a different type of angle that you're going to learn about in a couple lessons. Let's go here. Okay, here's my X. Here's my angle X. Do you know its intercepted arc? What would you name its intercepted arc, letter-wise? JL, right? Arc JL is its intercepted arc. So if we can find arc JL, we can find our angle.
Y opens up to QJ, and the other one's 180.
Okay, so you could go that route. We know Y is 55. So if we double that, that would give us this one. We subtract from 180. Anyone see a quicker route? Because there is one. How about with Q?
Oh, can we just
Double Q.
double 35?
Mm-hmm. So Q, this one here, opens up to JL, and if two arcs open to the same angle, if two angles open to the same arc, they are equal, right? So X is 35. Or you could just say, because this is 35, then the arc is 70. So arc JL being 70 means our angle X is half of 70, or 35.
Oh, wow.
Okay, so the nice thing about this problem is we just talked through like 3 different ways you could have done it, right? So you don't have to see the same way as everybody else. You just have to find one of them. Questions on that?